Welcome to another GC Basic demonstration. This is for the PIC18xxQ24 series. This one is specifically about timers and timer interrupts. So yeah, it's quite exciting, this one. Like and subscribe to the video, let it run all the way through, and then go back and like and subscribe it, obviously. Those numbers help, those metrics and numbers help the channel. So we're looking at timer 0, timer overflow, 8-bit timers, 16-bit timers to flash the LEDs. So up to now we've been using the internal calculations of the weight, and weight is based upon the frequency of the chip, and it's relatively simple to use. You just type in weight and a unit and a time unit. But we'll be looking at timers using timer 0. So I'm assuming you've got all these things in, you've got the software installed, you've installed the programmer, you've got a Q24 attached, LEDs are operating, pops, switches, and a USB TTL. We will use that in this because it's a useful thing to check the frequency. So I've changed nothing in the hardware. That's things of note, I suppose, because someone dropping in, I've got 4 LEDs on port B, and I've got on port C the transmit for the US art, and that will be configured via PPS to ensure that it works correctly. So first of all, we'll look at a primer for the timer. I'm a poet and I didn't know it. A timer primer, there we go. So we need to just have a little, make sure we're all on the same page. Okay, so timers can generate very accurate delays, whereas the wait command is an approximation based upon the number of cycles taken. The wait is actually going to be based upon an oscillator of various types. You can create your own delays and required delays within running loops and within your program. And these timers run independent of your CP operations. And there's two big parameters that you need to be aware of. One is called the pre-scaler and post-scaler, and we'll look at that. But a timer is nothing more than just a simple counter from 0 to 255 in some cases, and in other cases from 0 to 65535. And when it gets to the end of that, it generates an overflow. So for timer 0, you can generate an overflow. In other timers, you can do matches, and we'll look at those different options. But what you've got is this blue diagram at the bottom. You've got oscillators on the left, and you've got an interrupt on the outside, on the right-hand side, and I'll walk you through that. But what you need to do in GC Basic is to set it up is you need to give it some parameters. You need to use the command init timer 0, could be timer 1, 2, 3, or 4, depending on what the chip is. Where the source is, I'm going to be using the internal source, so that's oscillator, could be external oscillator, EXT. And then you need to give it what's called a pre-scaler and a post-scaler. And that's just the way that this one works. You need to add to it the clock source. So there's an add sign in the middle here, look. So you say init the timer, the clock source, the pre-scaler, the clock source, but they're added together to make a sum, and then you post-scale it. Start the timer and set the timer to a value, and it will do things. It will generate the interrupt at a regular interval. So if we look at how that works inside the chip, and I've lifted this from the actual datasheet, I'm using this clock source. You may decide to use another. Therefore, you can use some of these parameters, check the datasheet, and check the help in GC Basic. We need to set this one here, a pre-scaler. It's a value, it's a register. It's a register, therefore it's a value of 0 to 255. It goes through some synchronization and then what's called the timer 0 body, which I'll come onto in a moment. And so we need to put a number in here. We need to put a post-scaler value in. So we need to put a registered value in there. And as we previously said, we need to select our clock source. And we did those. Those are the 3 parameters. And you can set other things like whether the interrupt flag is set. And if it is, it will raise you an interrupt out on timer 0. It's very simple. But what goes on inside that timer block is dependent on whether you have selected an 8-bit timer or a 16-bit timer. In the old days, 4 years ago, most of the chips of this style only had an 8-bit timer, but they introduced a 16-bit timer. And depending if you're using an 8-bit or 16-bit, you need to put in a value into the register, into the timer register, and if it's an 8-bit value, you put a value of 0 to 255, and if it's a 16-bit value, you need to put a 16-bit value, 0 to 65535. And I'll show you how to do that, and it's relatively simple how you can actually change between these two. Okay, it's very simple, but you can change between the two, and you just need to give it I'll just erase those. You just need to send it the right parameter. So let's look at this accurate time delay. So you could choose an oscillator. This one example, I'm using the internal oscillator. It's called the clock select. That generates a little signal at a specific frequency, and you can send that into a prescaler, and that prescaler will essentially factorize or stretch that signal out, so that input signal becomes a longer signal, or the wave has changed. You can post-scale it, and you can make it even longer. You don't need to make it longer. You can have a post-scale of 1, which is 1 in, 1 frequency in, 1 frequency out, but it will change. It has the potential of changing the frequency. If you want to use the timer, you need to enable it, and then you need to set it to a value. And then you're waiting for a timer to overflow. So you have to set a value. I've set this one to B1, and I'm looking at this register here, whether it actually overflows, and it's currently 0. Well, this timer will increment. Every time the clock gets a clock signal, it will increment the timer counter. B2, B1, B2, B3, and then lots of other numbers, and it will end up at FE. And in this case, it's an 8-bit timer, because when it gets to FF, that's the 255 signal, it will overflow. The counter resets to 0, and it will then set our flag here. It will say timer overflow 1. And when that occurs, we get an interrupt signal, and we can test for these signals. And we go, whoa, we've got an interrupt. Now go do something, or do something, and we'll talk about the do something. So we're going to examine some sample code. We're going to look at some tools that are available, and we're going to just walk through it nice and slowly. So where have I got to? Desk cam. Oh, someone asked me what was Zen mode. This is Zen mode when you can see the 3 windows in here. Look, you can see the camera, the programming window, and the actual source code all at the same time. Now, I don't see that on my screen. Only you see that because that's the way that the camera's all hooked up here. So I call this Zen mode. It's when it's like a bit of a mystery what's going on to me. Okay, so I've left this with the reversible LED. So this is where we left it. We can reverse these things and we can change the frequency, and it's using the weight here. Okay, so I put that like that. There we go. It's just going backwards and forwards. I'll close that down. Control B to open up that side window. Select 110 rotate LEDs with timer interrupt, and we'll walk this code. Control B to shut that window. Now this is the entirety of the code. I have minimized it quite clearly, as you can see on the screen. I've selected the chip. Now I've selected 16 megahertz. It's like critical. You know what you're doing here. If you select 64, you need to have all your parameters, your timing parameters that go with that, because you need to calculate these things. Now, in here in the configuration, let me just expand that. How do I expand that? There we go. If I expand that, it's got all the things we've seen in the past. I've left the PPS for the serial in there because we'll be using that in a minute. And here's all the hardware stuff set up, all the constants set up because they haven't changed. look through those in your own time. Okay. So there's my hardware set up, and this is what I need to set up. So I need to initialize the timer. It's an 8-bit timer, and the first thing I'm sorry, I'm going to use a 16-bit to start with. There you go. That told me something. Initialize the timer. We are going to be using a 6-bit, so I just define this constant. Timer 0, 16-bit, and that sets a bit for you inside of the chip. And I'm going to send this command: init timer 0, internal oscillator with a prescaler of 64, clock source of divided by 4, and postscaler of 1. Oh, what on earth is all this, hey? I'll show you how to do it in a moment, okay? I'll come back to that, I promise you. I'm going to set the timer to a value 0BDC, and now we're getting into an interrupt. On interrupt, timer overflow. So there's an interrupt called timer overflow. Call a routine called call blink. What does that do? Let's have a look down the code. There's a function. We saw functions very early here, and all it does, it says the code has timed out. Timeout equals 1, and I have cleared an interrupt flag. But you don't need to, because it's done automatically by GCBasic. It will always come here when a timer 0 overflows. So start the timer. So 4 commands: initialize the timer, set the timer, on interrupt, timer 0 overflow, call the blink, start that timer, and it will run. And if I just program this to start with, we can see what's happening. It's just erasing the part, and it's programmed it. Now the frequency's changed to 1 second. How do I know that's 1 second? Before we go into the details of where I got the parameters from, I've left something in the code for you. Function key F9 brings up the terminal. Here's the terminal. Hopefully you can see that in Zen mode. There we go. And I have set in here a little flag called time. There's a little flag called time. And if I connect to that port, oh, did I actually do it in this one? Oh no, I didn't. No. I'm going to add it in for us here. Print a string. I'm just going to print a dot on that serial terminal. And because I've got time set in here on this little flag inside the terminal, it's going to tell me how often, the time it actually pulses. Oh, look at that, look. 50 every second. If you need to make it more accurate, you can adjust what's a register called OSC tune, T-U-N-E. Look in the data sheet. You can tune the clock, but as it changes temperature in here, I get a variation. But that's not bad, actually. And all it's doing in here, it's going through the timer that we set up, and it's saying, do it forever. If the timeout has occurred, so it's equal to 1, where did it get that from? It got that from the blink subroutine. It rotates it. It rotates the LEDs exactly the same as we did in the first video for 040. And then I just set the timer to 0 to say that I processed it, and then I reset my timer. Just set it again. So I've set it at the top, I rotate the LEDs, and then I reset my little flag called timeout, and then I reset the timer. So where do I get all these numbers from? Well, it says in here, you can use a tool like Mr. E Timer Helper. Oh, let's have a look at that. Well, that's in your installation. Trust me, it is. I'll open up another folder. So, GCStudio, GCBasic, demos. You'll have less folders than I've got, I can tell you. Right, I'm in the demos folder. Interrupts and timer solutions. Interrupt timed examples, and there's some calculators in here, look. What did I call? Which one did I say use? Mr. Oh, here it is, look. Mr. E Multi-Calc. It's in your folder, so you can just use it. Timer calc, take that option there, it'll put it on the screen for you. And you say, right, what frequency have I got? I've got a 16-bit frequency, 16 bits, and down the bottom here, it's just telling you what the frequencies are, etc. So it says down here, if you want a specific time, you would just adjust it. So pre-scaler, that's a 16-bit. I'm going to use a different calculator. I'm going to use this one. Select the PIC18, 16 megahertz, timer 0. I want it every how often? What did I set it to? 1 second? Every 1 second, that's 1,000 milliseconds. Calculate. It says in here, I need to set timer to the high value and low value, put them together, 0BDC. 0BDC is exactly the same setting. The rest of this you don't need, you just need these two. In actual fact, here's the preloading value here, look. The preloading value is here, which is 03, it's a decimal number, 3036. But in hexadecimal, B0BDC, and that's what value is in here. I've just set the timer to that. And it says in here, the prescaler needs to be, look, and it says you need to use a prescaler of 1 to 64. It tells you the values. You don't have to calculate these. You don't have to sit with a calculator anymore. I'll show you how to do an 8-bit in a minute because there's not many tools that do 8-bit calculations for PICs, and I've written one. So that's how it works. We say that we're going to use a 16-bit. We say that we're going to initialize our timer. We tell it on interrupt of an event. This event is called timer overflow, called blink, and then we start the timer. The moment the interrupt occurs, it gets passed down to blink. It sets a flag called timeout 1 and then clears this flag. Otherwise, it would never re-enter. Let me reassure you, you don't need that because GC Basic does all that. And then if we know that that little flag called timeout, which is a variable I set up, is it a variable? It's a bit variable. It then says, right, come into here, send out that string. Remember, the clock's still running in the background. It's running, exactly. It rotates the LEDs and then resets our timer for us. It's very simple. 4 steps. 4 steps. Initialize, set. If you need non-interrupt, do it. Start the timer. So there's 4 things in this case. So what else can we do in here? Good jobby. Was I going to show you PICInfo? I'm going to show you PICInfo. Open up PICInfo. I've got my PICInfo running. If you want to find out all the interrupts, select your chip, go to the interrupts tab, and here are all the interrupts in here. And there's lots of interrupts. In this particular one, it's timer 0. If I do a search on timer 0, it says timer 0 is overflow. It will automatically set this bit here, which is timer 0 interrupt enable, and it will automatically clear timer 0 interrupt F or flag. Those two are handled automatically by GC Basic. Hence, that's why they're in this table. Now we know that, we can do some other stuff. So we know that this flag is going to be set every time that interrupt happens. Cool. Let's look at example 120. Rotate the LEDs using an 8-bit timer. I've opened it up. Exactly the same header. I'm not even going to discuss it. Because we're going to use an 8-bit value, we're going to 8-bit timer, we need to do some clever stuff. We need to send it a value between 0 and 255. We'll get to where we get that value from. But it's the same, look. Interrupt, initialize the timer, start the timer, set the timer. And then in our little program down here, I've said wait for that flag. I'm not using an interrupt in this case. Wait for the flag to be set. Well, I'm waiting for here. It will wait until the flag changes. So it will get cleared. I clear it down here as my next instruction. But I need to do that quite a few times for an 8-bit timer because the range of an 8-bit timer isn't as big as a 16-bit, and I need to count it 100 times to make me my 1 second. So I say, if the timer, I have a little variable called counter timer, which I'm incrementing by 1. If that timer equals 100, then rotate the LEDs, put the dot on the screen. There is no subroutine. It's essentially saying every time I see an interrupt happen on that flag, increment timer counter, and when it gets to 100, do it. So let me just program it, then we'll see where we get the data from. It's going to increment the LEDs as it was previously in every second. There we go. Is that working for us? I'll clear that and connect that. So something is making that change every second. Let's have a look how it's doing it. Well, we need to set this timer here to a value which is actually 10 milliseconds because the range is not big enough. Because we're not using a 16-bit timer, we're using an 8-bit timer. We only have a range, a very small range. So what I did many years ago, I wrote a calculator. Again, this is in your folders. Let's see if I can find it in here. So I'm in the interrupt timed examples, and there should be a spreadsheet. There is a spreadsheet. Pick timer calculators. Open it up. You can use this in, what's it called? You can use this in IE, that will work, or whatever it's called. Right, my chip frequency, we know that I set that to 16. So anything in orange, you should be changing. You should be changing. And I want to get this to this time here, which is actually 10 milliseconds. So if I set that to 1 second, 1, I get red squares, look, because the range I've selected is not possible. So I have to sort of work through this and go, okay, if my clock megahertz is 16, yeah, so I know that, and my source divider is 4, that's FOSC 4, means divided by 4. This tells me that I can use a prescale of 256 and it will give me a value that is acceptable. I put 0.1 in there, 100 milliseconds, that's not, I want 10 milliseconds. So look, I could have chosen 128 doesn't work. These are the I'm changing the clock prescaler, it's red. 256 I know works because that's the way it was set up. 512 works, but the actual interval is getting quite inaccurate. So I just happen to know that 256 is a very good close estimation. No clock's going to be perfect, okay? And if you look down here, it says the value to use is 9C. You could pump it straight in, but it's 9C. It's calculated 9C for you. If you're going to code this in decimal, you'd use 339, that number. If you're going to use it and pump it in by hand, you'd use it's that you need to put it in the high byte. And so the value that we're going to be using is 9C, calculated automatically. And if you wanted a time of 0.005, 5 milliseconds, it says use 4E. So we know that we've got a little tool we can use to get these timers. Okay, it's fantastic, really, very simple. And that's where this value 9B came from. It came from that calculator. And then in our program, once we counted 100 times, guess what we do? We put the timer back to as it was. 9, so that's an 8-bit. And the only thing that changed to us is we had to put a different value of an 8-bit value inside the set timer. The rest of it is very similar. Prescale of 256, we got that from the calculator. Clock divider of 4, postscaler of 1. So we know it works. And there's many different tools that will give you these set timer calculations. And you can do it hardware as well. Control B. Rotate it using a 16-bit timer. Let's look at how that works. Same header. I'm not even going to discuss it now. How do I set this up? 16-bit timer. Well, if it's a 16-bit timer, we can use other calculators, and we need a value of 3036. In actual fact, we got that from the calculator as well. If we look in the spreadsheet, look, what's the prescaler set to? 64. Prescaler 64. What's the post scaler I've estimated? Oh, what time have I gone for? Oh, it's every second. So it's 1. Oh, this is 8-bit. I'm so sorry, I've done that wrong. That won't work. I need to use a different calculator for that. It's a 16-bit. So this is a 16-bit tool, isn't it? So the value in here would have to be 3036 as per this timer calculator. I'll go back to my source program. Oh, that's what I've got in here, like 3036. So that's a 16-bit timer because I've got an interrupt of 64. I've set it to 3036 decimal, and I've started the timer. Do you know what? That's it. Same program. It says, wait for the flag to be set. If the flag's been set, clear it. And because we've got an increased capability in the 16-bit timer, we can measure at 1 second. Guess what? When I program it, it sort of works. So I'll go out to the terminal. I'll clear it. I'll connect to it. And the only reason I got this terminal is so that we can see this timer. So it's the only reason I got it there. 41, 42, 43, 40. Do you know what? That ain't bad for military work. If you want more accurate, you'd use an external oscillator, and you'd have to set up the external oscillator, but very simple. Same command set, you would just change the oscillator here to external, and if I press function key F1 to bring up the help, it tells you in here what to do. If I come up to the help, it says my clock source can either be OSC, let me just zoom in for you, OSC for the internal oscillator or external. And it does work. And you can set all sorts of clocks up as your clock source. But you'd have to work on your how you set the value and calculate that. But extremely simple through the 3 commands that you need, which is init, start, and set, plus an interrupt handler if you want to add one. We'll call that a day. We are done with moving LEDs. Let me just look. We see no more LEDs moving after now. We're going to go into EEPROM, how we show EEPROM values on the serial terminal, and that will give you more more insights into how things work and the capabilities. Now, wait a minute. Do we have EEPROM on this chip? Let's just check. PICIt Plus. Wait a minute. Oh, we do have EEPROM. That's okay. I was working on a chip overnight which didn't have EEPROM, and that sort of, oh, you can't see it. That sort of worried me. How do I know it? Because look, it's got this down here. It's got looks like 256 bytes of EEPROM. If I hover over the name of it, it says it's got 512. You might not be able to work that out, but anyway, good. We're doing EEPROM, and we'll call that a wrap.